Now, I've said that most of our day-to-day functions are continuous, which is true. Um, One way that we do see continuity, or one easy way to have continuity, is with piecewise defined functions. It's very easy for piecewise defined functions to have discontinuities. Let's let f of x equal x squared minus 1 when x is less than or equal to 2. And let's let f of x be x plus, well, not that, x squared plus 1 when x is greater than 2. Now, x squared minus 1 is continuous because it's a polynomial and all polynomials are continuous. Similarly, x squared plus 1, that's a continuous polynomial. But if we look at the graph of this function, there is a jump. There is a discontinuity at 2. 2, remember, being the joint, being the place where we change from x squared minus 1 to x squared plus 1. So here's sort of the classic homework test continuity problem. You're given a piecewise defined function, and you're asked whether it's continuous at the joint. In this case, at 1. And, problems like this are popular because they evaluate a bunch of stuff. They evaluate continuity, but as part of that, they also evaluate one and two-sided limits. So what do we need to be continuous at 1? Well, we need f of 1 to exist. Better change one of those. So f of 1 is defined. We're in this piece because 1 is greater than or equal to itself. So f of 1 is 1 squared minus 2 times 1 plus 5 is 4. And now here's where things get more interesting. We need the limit as x approaches 1 of f of x to exist. And if we're talking about the two-sided limit, it's maybe hard to just look at this and know. Does this exist or does it not exist? But a way we have of answering that question is that the two-sided limit exists if the one-sided limits are equal. And evaluating the one-sided limits is a piece of cake. Now, I should not say that. It's not a piece of cake necessarily if you're learning this material for the first time. But if we're approaching 1 from the left, then we're less than 1. And if we're less than 1, we're in this piece. So we're taking the limit as x approaches 1 of 3x plus 1. And 3x plus 1 is a polynomial. We can take its limit by taking this and 1 and plugging it in. 3 times 1 plus 1. This is 4. Then the limit as x approaches 1 from the right. Well, for approaching 1 from the right, we're bigger than 1. We're in this piece. So we're taking the limit as x approaches 1 of this polynomial. And once again, the limits of polynomials, we just take the number and we stick it in. 1 minus 2 is negative 1, plus 5 is positive 4. These numbers are equal. The limit exists. It equals 4. And then the final continuity condition. The limit as x approaches 1 needs to equal the function evaluated at 1. And the limit as x approaches 1 is 4. And f evaluated at 1 is 4. And 4 does equal 4. Check. So this is an example of a piecewise function that is continuous at the joint. It is continuous at 1.